So, let's talk about rotational elements again. So we're like in this part of this course where I give like the same lecture 4 times in a row and see if anybody catches on. I give the same lecture 4 times in a row. It's just that we're doing different energy domains like rotational circuit or rotational elements, translational mechanical elements, electrical elements, and then just generalizing them. So like it's the same lecture and it's a little boring, but it's supposed to be boring. If it's boring, that means that like you're getting the fact that they're analogous, and this is almost like superfluous. We don't even really need to do this. We could just say, they're all like this. We do need to do it because we like good form, go through all the details. So we talked about rotational springs last time. Rotational springs, as you might recall, are springs that if you twist them, they resist with a torque that's proportional to the angle of twist. And then we talked about the different types of power flow variables for rotational systems. One of those power flow variables was the angular velocity. Do you guys remember what the other one was?
Torque?
Torque. Yeah, because the product of the torque and the angular velocity is the power. Product is the power. So, then we talked about the rotational spring. Now we're going to talk about the rotational moment of inertia. Recall that the rotational spring was an energy storage element. It stored energy in elastic energy of the spring. Moments of inertia store energy in their momentum. So a moment of inertia element with moment of inertia J, angular velocity omega, which is always relative to an inertial reference frame. We'll talk more about that. And angular momentum H has the constitutive equation that the angular momentum is equal to the moment of inertia times the angular velocity. Okay, probably a familiar equation. If you take the time derivative of this equation and rearrange it, so omega dt is the angular acceleration, but we want to leave it in terms of omega because that's a power flow variable. dh dt, the time rate of change of the angular momentum, is defined as the torque. So we can just write that the time rate of change of omega is equal to 1 over j times the torque. So let's look at this figure here. You see that this is how it's represented schematically. We have this moment of inertia. We have this shaft port here that we have a torque going into. And we say that the angular velocity of J is just omega 1 minus omega 2, where omega 2 is always constant, often 0, but always constant. It has to be an inertial reference frame, because this is just Newton's second law for angular systems, for rotational systems. That's the torque is equal to the moment of inertia times the angular acceleration. You guys probably saw this as T equals J alpha back in dynamics class, because we don't use alpha because we want to write it in terms of omega. Any rotating element with mass can be considered as a lumped inertia element. The flywheel is a quintessential example. So a flywheel is an element that can store mechanical rotational energy, right? So you can spin up a flywheel and it can actually store quite a bit of energy. It's not a great way to store energy because it's leaky, right? Unless you have like air bearings, and then you still have a little bit of drag on the thing, but it's going to spin down, right? And it's not even that long that it takes. It's useful. Flywheel is useful for some systems, but they're pretty rare these days. Used to be more applicable. they store energy in their angular velocity. So we call them energy storage elements. But let's think about, so the flywheel, yeah, okay, we don't see a lot of flywheels we do see flywheels occasionally, but we don't see a ton of them in our systems now. What is another reason we would want to define a moment of inertia besides like an actual flywheel element? Anybody think of a situation? A gyroscope can have an actual flywheel in it. There's a lot of like solid state ones now, but yeah, those ones are cool ones with the flywheels in them. There's also, so for instance, you might have, say, a transmission that has a lot of gears in it, right? The gear has a reasonably large radius compared to the diameter of the shaft, which is not uncommon to see. You might need to take into account the moment of inertia of that gear. And ideally a gear has no mass, but we know that that's not true. So we could put in a moment of inertia element in the system on the shaft, like right before it goes to that sort of ideal gear, to model that effect of having some inertia in the gear. Okay. Yeah. So that is all for moments of inertia. We're gonna do a lot of examples soon, but like we can't do that much with these yet, so I'm not doing examples because it's kind of boring when you're like, just look at the problem but can't do any maths with it. So we'll be doing maths soon. Don't worry. I know you're getting bored without all these maths. Like we're missing out, but soon we'll be back to them. Rotational dampers. So we talked about springs and inertias, and those are both energy storage elements. This is going to be an energy dissipative element. Defined as elements for which the torque through the element is a monotonic function of the angular velocity across it. Linear rotational dampers have constitutive equation, and turns out elemental equation as well, that the torque is proportional to the angular velocity. Okay, so the proportionality constant B is called the torsional damping coefficient. Linear torsional damping is often called torsional viscous damping because systems that push viscous fluid through small orifices or those that have lubricated bearings are well approximated by this equation. For this reason, a damper is typically schematically depicted as a drag cup or as a bearing, both of which are shown on this figure. So let's take a look at this figure. We've got two different schematic representations here. And these are the two most common. There can be some other variations of it, but here are the two most common. So you have a torque that's transmitted through here, and each side of this can have a different angular velocity. So this upper one is called a drag cup. And this is really useful for certain applications when you want to have the two shafts be coupled at high speeds, but at low speeds they're not really that coupled. So it's a sort of it's a useful thing to have is this ability to transmit the velocity or the torque when you have high velocity, but not when you're at low velocity. So there are some applications of that. It's pretty nice little mechanisms. And those are actually discrete elements. You can get drag cups to put into a shaft. It's not just an approximation of something. And then we also have this bearing representation here. And this is, if you go through a bearing, the shaft doesn't change velocity on each side. It has one velocity. The shaft has one velocity through it. But the bearing is typically housed with connection to the chassis, right? So the bearing connects to the chassis. So the other velocity with a bearing is usually 0, or whatever the chassis angular velocity is, which is, 99.99% of the time is going to be 0, right? You don't want your chassis typically to be rotating. It'd be weird if it was. So this is the representation for a bearing, which is pretty well approximated with this model. So the reference in this case is going to be to ground or to the chassis velocity. Linear damping is a reasonable approximation of lubricated sliding, but rather poor for dry or Coulomb friction. Those forces are not very velocity dependent. Rotational dampers dissipate energy from the system, typically to heat, making them energy dissipative elements. So very, very analogous to a linear or a translational damper, but for rotations. Torque and angular velocity sources. So we have one more thing to define, and there are sources. So you can have a torque source that supplies an arbitrary torque, whatever you specify, and it will adapt to whatever angular velocity is required to make that happen. Similarly, you can have an angular velocity source that you specify an arbitrary angular velocity, and the source will supply whatever torque is necessary to make that angular velocity happen. Now, you can't buy these off the shelf either. Well, to a point, right? You can buy a motor that has, well, there are different uses of the term servo motor. Some people will refer to a motor that has a controller on it. You can specify the speed of the motor, for instance, as a servo motor. And so a servo motor in that sense is essentially an angular velocity source within some limit, right? Because at some point it can't provide the torque necessary to make that angular velocity happen, but it tries to. Like if you say spin at 500 RPM, it tries to spin at 500 RPM. It might not be able to actually spin at 500 RPM, but it tries to. So it approximates an angular velocity source. You can also control the torque too. So you can have a motor that you're controlling the torque for. And those can be considered to be torque and angular velocity sources. Now, we're going to model the internal workings of the motor from the electronics all the way through to the torque and angular velocity. So we're not going to well, I should just say we look at motors not typically as being sources. Typically we think of them as being part of the system, and we model their internal dynamics. But you can consider a controlled motor to be a source in certain applications, which does happen. I mean, you might have already designed your motor with a controller, and then you have another system that you're going to use it with. So you treat it as a source that can provide the necessary velocity or torque. So we'll a lot more on angular systems and motors and torque and velocity. There's going to be a lot more of that, but now we have an idea at least of what type of system elements there are and the analogies we're going to draw soon to electronic systems. Any questions on these before we move on? Okay, so